Welcome to Astronomy. Alright, so Earth and the universe. This is going to be our first topic. What I'd like to say is when you're thinking about this unit, brand new unit now, start thinking we're going to go huge down to small in terms of our objects in the universe. So let's then start thinking huge. So Earth and universe, well, we're extremely tiny, but let's just start with in terms of timing. Right now we believe, based on a lot of measurements in astronomy, pointing our telescopes deep into space and analyzing a lot of the light in space, we have determined that there was a Big Bang, aka the Big Bang Theory, not from the TV show, all right? And that means that there was this giant concentration of energy all located way back in the past, about the size of a grapefruit, and it exploded, and everything and anything and all that ever was and ever will be is already there. Yeah. So that's the Big Bang. I'll put a link to Big Bang Theory if you want to check out something else a little more in depth. All right, but eventually the universe cooled down over time, over hundreds of thousands to hundreds of millions of years, cooled down, and those atoms started to form. Those atoms started to form molecules. Those molecules started to form substances, and those substances started to create massive amounts of mass and matter. Eventually you started getting stars and planets, and eventually galaxies. And so that's sort of where we are in terms of today, our modern universe, what we currently think of as the night sky. All right, evidence for the Big Bang. A lot of this evidence for the Big Bang was identified by Edwin Hubble, which the Hubble telescope is named after. So, how do we determine that there is a expansion or a movement of everything away from one another into this infinite void called the universe? Well, we look at their spectrum. Okay, so they all give off light, and light is part of a spectrum. And within that spectrum, we can break them up by frequencies of color. Okay, we can also look outside the visible spectrum at other wavelengths to determine whether or not something is happening in the universe. So light tends to give us a lot of evidence. We have to do some measurements and computations with it, but we will be able to determine more information from this light. Now, all colors together, if combined, is a white light. That's what we refer to it as. And then it can be broken up into the spectrum. So let's talk about what happens if something is moving at extreme speeds away from us. And by extreme speeds, we are talking about extremely fast speeds. We're talking about hundreds of thousands of kilometers per second. Okay? Very fast. And at those tremendous speeds, there will be an impact on the intensity of light. The speed of light doesn't change, but the intensity of that light does change. So I've got two balls. I've got a red one and I've got a blue one. Okay? Or at least the tiles on them are red and blue. We're going to utilize these as if they were our color spectrums for this example. So our example that we're talking about is the Doppler effect, meaning that if we have light that is moving towards us, or an object is moving towards us at tremendous speeds, that light will start to bunch up. So the energy starts to bunch up into higher frequencies. So as something's traveling towards you, you end up having a blue spectrum coming at you. Okay? And if it's moving further away, it ends up being red. Okay? So let's think of it this way. If I were to be moving towards an object, I'm going to be able to increase the intensity if I'm walking towards it and throwing it. So, like an asteroid, like a galaxy, or like a planet, there's movement towards you and it increases the intensity of that light. The opposite is true. So if I'm walking backwards and I throw it at the same amount, I'm not going to be able to have the same impact when that light gets to me. So even though I'm throwing the ball at the same speed, depending on whether I'm going back or towards it, that will impact the intensity at which my light, the ball, impacts or reaches a surface, or our case, telescopes. So in terms of a redshift, it's less intense, meaning that the object is moving very far, very fast away, and that light is having less of an impact when it gets to us, even though it's going at the same speed, just like how I threw the ball at the same speed. Now, if it's coming at us and I throw it at the same speed, the speed at which I am moving, in addition to how fast I'm throwing it out of my arm, increases the impact. So higher intensity. That's probably the best way I can show you right now under the current circumstances. So let's take a look at what this does to these things. You probably have not seen these before, but let's pretend for a moment that you visualize in your mind a prism. And that light passes through the prism and it uncovers all the different colors of the entire rainbow. Think of this as if it's the entire rainbow from violet to red. And we, when we observe stars in a visible spectrum, can see those colors when we break them up. But if we use really, really fine-tuned spectrometers, we can see, or a spectroscope, we can see the barcodes of elements that are in this star. And if you're interested, feel free to sign up for Astronomy next year or the year after so we can talk more about how these dark lines form, okay? And how they are used. So for now, think of these lines as if they were barcodes. And those barcodes are going to tell us what element is there. So let's, for the moment, pretend that this barcode here is for the element hydrogen. Okay. Now, if this star, or these stars in a galaxy are moving rapidly away from us, then these barcodes will shift to the blue spectrum. So you have a blue shift if it's moving towards us. Oh, geez. You can tell I've done a few of these videos. If the object is moving rapidly toward us, then you will get an increase in intensity. These lines shift to the blue. Oppositely, if it's moving away rapidly, extremely rapidly, the intensity decreases. So the original lines shift to the right. Now you're going to say, but Mr. Ryan, how do we know whether it went right or left? We don't know what it started with. This is what we do in the laboratory. We take hydrogen and we get it really excited in a tube, a vacuum, with just that gas, and we throw the electricity on and we observe what the barcode is for that element. So we know where it should reside in a static motion where it's stuck. One place and we're observing it. Then we can determine, when looking into space and analyzing their codes, or these spectral lines, we'll be able to know whether it has shifted to the blue or to the red. Another example of the Doppler effect is when you have an emergency vehicle, like a fire truck, police car, ambulance, anything with a siren, or even just a really loud vehicle is coming towards you, it gets louder and louder and louder, but the speed of that car might stay the same. However, as it gets closer, it gets louder and louder and louder and louder, and then it passes you, it gets quieter and quieter and quieter and quieter and quieter. That would be an example of the Doppler effect. Instead, we're saying that the intensity and the wavelength of the sound is bunching up as it approaches you, and as it passes you, that elongates and gets less intense the further away this vehicle gets. So also, let's keep in mind that a few things in terms of what you should have been annotating as you're going through. Universe 13.8 billion years old, Big Bang Theory, talk about spectrum, red shift, blue shift for the Doppler effect. All right, let's talk also about how the universe is made up and what are some of the objects that are in the universe, and biggest to smallest. Universe is the biggest. Next down will be our galaxies. You do have an in-between called a local group. That's a bunch of clusters of galaxies. So you've got universe, galaxies, nebula. Nebula are giant dust and gas clouds that help produce stars. So then we've got stars, which are like the sun, planets, moons, asteroids, and comets. So that is respectively largest to smallest for objects that we're going to be concerned with in Earth science. All right, so we're going to pause here. And, we're not going to pause here. We're going to continue to talk about the Milky Way galaxy. So let's drill down a little bit deeper. All right, so our solar system resides in the Milky Way galaxy. So a galaxy is a combination of millions, maybe even hundreds of millions of stars with their own planets and their own moons and all that crazy stuff. So a lot of the questions you'll have are, Mr. Ryan, could there be life elsewhere? Maybe in a WebEx or maybe in an adulting club conversation, we can do a little more of that, or if you join me in astronomy next year. But there are maybe 100 billion stars in a galaxy. And in the universe, there's at least 100 billion galaxies. You do the math, that's a lot of zeros. For the potential for the number of stars, and then they may all have their own planets. May have all their own planets. So within our within our universe is the Milky Way galaxy, which we are a part of. So our star, the solar system, resides in the Milky Way galaxy. All right. There are three main shapes to galaxies. We have spiral, elliptical, and irregular. I've also mentioned up here there are barred spiral. We, the Milky Way, are spiral galaxies. Hard to see in this image on my screen. Let's see if I can try to get a different color here to help. They have arms that come off. Let's see if I can get another color to help with this. That's probably better. All right, so there's a rotation to this with spiral arms. All right, so one other important note, we've talked about this in electromagnetic spectrum, 3.18 times 10 to the 8th meters per second, that's the speed of light. That's going to be very important down below, but let's talk about the Milky Way. We don't get to leave the Milky Way to take pictures. However, we have evidence of how certain areas of our disk that we can see in the night sky has different velocities, thus helping us kind of determine that we have sections that are arms, okay? They come off the central nucleus, this bulge here of our giant central black hole. So here we have our disk. There is kind of like a halo that's around this thing. You have things called globular clusters, which are giant clusters of 100,000 plus stars. We have distance, and it's given in this new unit here called light years. So we've got a thickness for light years. We've got some information about how many light years are here from the sun's location to the center of the galaxy. We have the entire width of the entire galaxy, but it's not in a unit you're familiar with for distance. So a light year, let's break down what a light year means, okay? But let's do that by first talking about our most basic astronomical unit, which is literally an astronomical unit. That's a distance from Earth to the sun, which on average is about 93 million miles. So when we're talking about that, we're talking about a vast amount of miles. Now, a light year eclipses that, completely eclipses that. So light year, think of the speed, 3.18 times 10 to the 8 meters per second. That's very fast. So as we recall back from electromagnetic energy, that means light can go around Earth's circumference 8.5 times in 1 second. Now imagine how far light would travel in 1 year if it goes that fast in 1 second. Okay, so that's dictating the idea of how big a light year is. Now imagine 100,000 light years. So that means it would take light 100,000 years to travel from this side of the galaxy to this side of the galaxy. If your minds aren't blown at this point, well, I don't know what will. So after we understand light years, we can start to talk about the fact that if it takes 100,000 years for light to get to us, that means it left its destination 100,000 years ago. So the light that we're seeing is actually the past. I mean, technically right now, the light you're seeing from your screen that's entering your eyes right now is technically many billions of a second in the past. So you're not actually viewing me instantly, because the light from your screen takes the slightest, ever so minute and minuscule microscopic amount of time to get to your eye. So technically you see everything in the past. You even hear me in the past because sound is even slower than sight. But yeah, we can see into the past. So then you're like, but Mr. Ryan, can we see dinosaurs? We can't see our light. We can see the light coming from everywhere else in the universe. That's actually part of the way we've calculated the age of the universe. We took Hubble and pointed it in deep space for weeks to collect light and determined that we can see about 13.8 billion years in the past. There are newer telescopes that we're using, microwave, X-ray, and gamma radiation telescopes to help us see even deeper than visible light. But that's how we come up with that. So we're saying literally we are seeing right back to pretty much the Big Bang. So when we're looking at the sun, we're looking at the sun 8 minutes in the past. It takes 8 minutes for light to travel from the sun to you at Earth. You might have to rewind and watch that one again. It's quite a bit of information to take in. But either way, we call that look back time, or LBT. All right, so that's your introduction to the universe and galaxies. If you could, please go into your folder, open up your Universe and Galaxies Guided Independent Practice. Pause the video to ensure that you can try to work on question 1 and 2, and we will be back soon. We're back. All right, so the diagram below represents the spectral lines from the light emitted from a mixture of two gases or two gaseous elements in a laboratory on Earth. So here we've got those barcodes. We don't know which elements they are. We may not need to know, but we know that that's what that means. If the same two elements were detected in a distant star that was moving away from Earth. If they're moving away, they're less intense. So, let's see, less intense. Nothing about less intense yet. We do know though if it's less intense, it turns red. So maybe the entire set of spectral lines shift to the red. The spectral lines of the shorter wavelengths would move closer together. No. These never move. They stay like a barcode. You don't pick up an item at the store and you watch the barcode slide around, do you, on the UPC? No, they stay in place. So it would be best choice 1. They are all moving to the red because that's less intense. All right, let's look at question number 2. All right, base your answer to the question on the diagram below and your infinite knowledge of Earth science. The diagram represents the model of an expanding universe. So we've got expanding universe, we've got present day, and then we've got the future. Big Bang! Universe first formed. All right, so question 1 says, identify one piece of evidence that led astronomers to infer that the universe is expanding. galaxies are experiencing redshift. They exhibit it. They show us that they're moving away, and redshift means expansion. All right, so we're at that same place that we always are, giving you a few opportunities to see how these work. Use your access points. Get through the rest of this independent practice. What you will see, I've done a pretty good job with this one because it was available. I've got one image and 3 questions that go with that image to show you a little more like it's going to be in the Regents now that we're getting even closer to Regents time. All right, so again, if you need me, feel free to throw a comment down below with a question. I'm happy to hear them. WebEx, we'll meet up, and also on Google Classroom. So thank you. Bye.